Hello, welcome to this video. Today we're going to talk about fields. So, fields are pretty much the first thing you learn after after doing math, after graduating tests and all of that, and heading into university. The first thing you learn in linear algebra, at least, is fields. They are essential in mathematics to understand how numbers interact with each other and how they work in the big space of math. So first of all, let's begin by the definition of a field. So for a field, we need a set of numbers, finite or infinite, and we also need to define a sum and product for them. A sum doesn't have to necessarily be specific. The sum that we all know, like 1 plus 1 is 2, we could perhaps define a certain field where 1 plus 1 will be 3. It depends on how we define our sum. Same with the product. Same with the product. 2 times 2 in a field might equal 3, depending on how we define the product. We normally define the sum and product with our regular sums and products that we know. And because in fields we usually just talk about numbers and not really objects. Fields, although you could. But we're going to focus on numerical fields. So now that we have that, let's begin. And all of these sums and products are towards the field and not the regular sum or product. So a field, we want it to be as close that we can to our regular numbers that we know, and that we won't get confused with other things. So, at least the way I learned it, there are 7 rules for fields. Number 1 is closure. Closure. If A and B are in our field F, then also A plus B and A times B must be in F. Second is commutativity. If A and B are in F, then A plus B is equal to B plus A, and A times B is equal to B times A. We must be able to switch between the A and the B, and the result shouldn't change. The third one is associativity. If A, B, and C are in our field F, that means that the order of summing and multiplying shouldn't matter. That means that A plus B, so if we sum first A plus B and add C to that, that's the same as if we first of all add B and C and then add A to that. And the same with the product. First of all, multiplying A times B and then times C shouldn't change if multiplying A by the product B times C. Now the fourth one is identities. Additive and multiplicative identities. So this says if A is in our field F, that means that there have to exist a 0 and 1 in our field F. They have to exist no matter what. Such that A plus our 0 is still A, and A times 1 does also remain A. And also, 0 has to be different than A. We can't have the additive and multiplicative identities being the same number. Next is additive inverses. So if A is in our field F, that means that we're going to call it negative A is in F, such that A plus negative A is the zero of the field. It's the additive identity. And the sixth rule is similarly a multiplicative inverse. If A is in our field F, but is not the zero of the field, I'll later talk about why we can't have it being zero. That means that the inverse of A is in the field, which means that A times the inverse of A is the one of the field. And finally, we have distributivity as our last rule. And it's the rule that really connects the sum and product. Because as you saw, from all of these rules, we couldn't really connect them. This is the one that includes both of them. So this states A times our sum B plus C. So we can distribute this and get that this is the same as A times B plus A times C. So these are all the rules that should apply if you want a certain set of numbers with a defined sum and product to be a field. Now, let's go on. Let's quickly talk about why we can't have an inverse for 0. Okay, now let's talk about why 0 can't have an inverse. So if you play around with sets and try to make them fields, you'll notice that when you do get a field, no matter which field, you will always have that 0 times any number will still be 0, or that product is of course from the field. So you might think that for each field you will always have that for some number A in the field, you always have it A times 0 is 0. Is that true? Now, I'm going to spoil the answer now. Yes, it is true. And furthermore, we can also say that if we have, furthermore, if we have A and B in a field F, then this statement we're now going to prove is always true. A is 0, or B is 0. If you don't know, that is a symbol for a mathematical OR. So A is equal to 0 or B is equal to 0, obviously from the field. If and only if A times B is the 0, which will tell us that 0 can possibly have an inverse. So, first of all, let's begin with this side. We want to show that if A is 0 or B is 0, then A times B is 0. So, because of the symmetry between A and B, I'm just going to assume, let's assume A is equal to 0. And that will tell us, and now we want to show that that A times B, which is 0 times B, is 0. So let's begin. So we have 0 times B. What do we do with this? Well, 0, the only thing we know about it is that it's the additive identity. So we'll try to use it to prove this. So the additive. So the additive identity tells us anything plus this will give you the same thing. So 0 is the same as 0 plus 0, because we'll be able to remove one of the zeros as it's the additive identity. So we can say that this is our 0 plus 0 times b. Now, that by distributivity, we can take this out to get 0 times b plus 0 times b. Now, this already looks close to done. I mean, all we have to do is subtract 0 times b from both sides, and we'll be golden. We'll get 0 times b is 0. But we need to be careful, because who told us there is a number that when you add it to 0 times b still gives you 0? Well, that is true, and here's why. 0 is, by its definition, 0, of course, is in the field F. It has to be. And we define b such that it's in the field F. So by closure, 0 times b has to be in F. But because this number is in the field F, if we just look at it as a number in F, that means there must exist an additive inverse to this number. That means that negative of 0f times b does exist in F, such that the sum of these two is 0. So all we need to do is add that to both sides. So we get 0. So we get 0 times b plus the negative of 0 times b, its additive inverse, is equal to, well, erase this. This is equal to this plus negative the inverse of 0 times b. So this is 0 times b plus 0 times b. And that is plus negative 0 times b. Now, we know that we can move this because the order doesn't matter by commutativity. The order of summation does not matter. So that means that, first of all, this is something plus its additive inverse. This is, by definition, our 0, and this is our 0 times b plus 0 times b plus its negative 0 times b. Now this thing, just like we looked, just what we saw, that's what we saw just now. This is the additive inverse. By definition, anything plus its additive inverse, it's the 0 of the field. And now anything plus the 0 of the field, because this is the additive identity, by definition, this stays 0 times b. And we've just shown that 0 times anything is 0. And of course, the same thing we can do if b is equal to 0. Because if b is equal to 0, all we need to show is a times 0 is 0. But then we can switch around the order, and we'll have the exact same thing. 0 times a is 0, which we've just proven to be 0. And by the way, note just how many properties of a field we used just to prove this one. Only one direction of the proof, which says something times 0 is 0. Okay, now let's erase this and move on to the second part of the proof. Okay, now let's begin the second part of the proof. So we want to show that when we have A and B in our field F, and we're also given that A times B is our zero of the field, we want to show that either A0 or B0. There are a couple ways to do this. We could go contradiction, we could go cases. The cases are always shown. These are cases of a proof. How about I do a proof of contradiction? So I'll do contradiction, which basically means that I'm assuming that what's happening is not, it's not the case where A0 or B0. So it's the case where A isn't 0 and B isn't 0. This, if you don't know, is the mathematical symbol for AND. So now let's begin. So this is an assumption which will prove wrong. So we're assuming A isn't 0 and B isn't 0. That means that by the definition of the field, the inverses of A and B both exist. So this tells us, so this means the inverse of A and the inverse of B are in F, such that multiplying by each one will give us the one of the field. So now that we know that the inverse of A and B exist, let's multiply by both on both sides. So we're going to multiply by the inverse of A from the right and by the inverse of B from the left. Because we're not always working with fields, it should be specified from which side you'll multiply. Because sometimes you can't necessarily switch the terms in a product, and that the order doesn't matter and all of that. So we're going to do the inverse of A times B times the inverse of B is the inverse of A times A. And we're going to do it so we're first multiplying this, the inverse of A, that, and then times B. This is the inverse of A times 0, and then that times the inverse of B times. So we've just proven anything times 0 is 0. So we know that this is the 0 of the field times the inverse of B. But again, we've proven that anything times 0 is 0. So we know that this is also 0. But now let's look from this side. So first of all, I won't do the entire process because it's just long and a bit annoying. But we can switch the terms here by commutativity. And then we'll get the inverse of A times A, which is the one of the field, times B. And that will leave us with, so I can just say like these sort of cancel out, which will get us the one of the field times B. That times the inverse of B. But the one of the field is the multiplicative identity. And so it doesn't matter when multiplying. And so we get that this is B times the inverse of B. But again, anything times its inverse is the one of the field. And look at this. We just got the one of the field is equal to the 0 of the field. And that's a contradiction. As in the identity rule, we also needed the 1 and the 0 to be different numbers. So this is a contradiction, meaning that this cannot happen, meaning that either A is 0 or B is 0, or of course both of them. You could also, by the way, prove this with cases. So you could by the way, even though we prove this with contradiction, we still can, you also can prove this with cases. So you can say, well, if A is 0, we're done. If A is not 0, and then do a small chain of algebra to show that B must be 0 if A is not 0, which will tell you that either A is 0 or B is 0. But that's how I proved it, and now let's move on to an example of an actual field. So this is the next example that we're going to see of a field. So this is Zn, which is the set of all remainders after dividing a whole number by n. All the remainders for such a number are just 0, 1, up until that number minus 1. So Zn is 0, then 1, all the way up to n minus 1. And now, of course, a field is not just a set of it's not just a set of numbers. We also need to define a sum and a product. So we're going to define A plus B, and I'm going to use this line above the 0 so that we can tell if I mean the plus of Zn or just the regular sum that we know, like 1 plus 2 is 3. So A plus B in Zn is the regular sum A plus B mod n. And if you don't know what mod n means, it basically means take this number, divide it by n, look at what's the remainder. So 13 mod 5 is 3, because you have a remainder of 3 after dividing by 5. 14 mod 2 is 0, because after dividing 14 by 2, you get a remainder of 0, because 14 is divisible by 2. So this is the sum. If the product is very similar, the product is the regular product, also mod n. So now we want to show that this is a field. But I have some news. This is not always a field. This is actually a field if and only if our n that we chose is prime. I'm not going to do it. If you want to, you can try. But Zn is a field if and only if n is prime. But still though, let's look at 2 examples of this type of Z. So let's look at Z5, and by what I said, 5 is prime, so yes, Z5 is a field. And this is 0, 1, 2, 3, 4. So if we what we want to do is find, let's do a couple of examples. So for example, what is our 1 plus 2? Well, that's going to be our regular 1 plus 2 modulo 5. So that's 3 modulo 3 mod 5, and that's 3. What is 2 plus 3? Well, that's going to be 2 plus 3, which is 5. Modulo 5, that's 0. That's our 0. But notice, that does not mean it's a contradiction. It means 2 is the inverse, is the additive inverse of 3, and vice versa, because their sum is 0. So, just as an example, negative 2 is 3 in the field. And because it's in the field, just so we all know it's in the field, I'm also going to put a line above these. And there also should be a line really above all of these 1, 2s, and 3s, but I'm too lazy to do that. just so you know, these are in Z5. And how about we do, what is 3 times 4? This is 12 modulo 5, which is 2. 12, after dividing by 5, you get a remainder of 2. So this is 2. So again, this doesn't lead to any contradiction that the product of two numbers gives a smaller one, because we didn't define any of big or small. So this also does not lead to any contradictions. And you can check 1 by 1 or by 5 is prime or whatever you want. Z5 is a field. Now, let's move on to a slightly different field. How about Z12? So Z12 is 0, 1, 2, and all the way on up to 11. The remainder is after dividing by 12. Now this is not a field. And here's a little insight too, so you can see, and maybe a little step in the direction of why this is a field if and only if the index here is prime, which in this case it isn't. Because, well, let's look again. What is 3 times 4? I'm going to put the lines here this time. So what's 3 times 4? Well, that's 12. But modulo 12 is gives us the 0 of the field. Does this lead to a contradiction? The answer is yes, because we've proved that for any field, if you have a product of two that's a product of two numbers that are in the field that gives you the 0, that means that at least one of them has to be 0. But in this case, they both aren't 0. 3 isn't 0 and 4 isn't 0. And that means it's not that we got it doesn't mean that we got a contradiction in mathematics. It means Z12 is not a field. And you can also check to see through the rules which rule does Z12 not obey to make it not a field. And so this is a little also insight about why it can be prime, because if it's not prime, this is a field if and only if the index is prime, because if the index is not prime, then you get something like this, because if it's not prime, it's composite, and then you get stuff like this, which leads you to showing that it's not a field. So that's one direction of it. If you want to, try to do the other direction. But this is another type of set that's it's sometimes a field, sometimes not. But what the thing is here, it's a finite set. You can count up the numbers here and get to a finite number. So in the Z5 that we looked at, there were 5 terms. And it can get a little bit confusing, because you think, well, we can always just add on numbers and numbers, and we'll get an infinite amount of numbers in the set. And it seems true, but it's not the case, because we've shown something like Z5, there is no big or small, because adding on, because you also always do modulo 5, so it would always be a remainder, 0, 1, 2, 3, or 4. So now let's move on from our finite sets to actual infinite sets. Okay, so now let's look at infinite sets and see just whether they are fields or not. So, is the set of natural numbers, is the set of natural numbers a field? This is the set. I'm not going to include 0, but it doesn't matter if we include 0, because it is not a field. 1, 2, 3, and so on forever. That's not a field. at least not with regular operations of sums and products, because we don't have inverses. So if you try to check the inverse of 2, you don't have a negative 2 because it's only the natural numbers. Okay, so if not natural numbers, how about the whole numbers, z? That is stuff -2, -1, 0, 1, 2, and so on. The whole numbers. Is this a field? Well, no. Yes, we took care of the 0, the 1, and the inverses and all of that, but the additive inverses, but we didn't take care of the multiplicative inverses. So if you check for 2, there is no half, such that you multiply it and you get 1. So let's write this. Not a field. This is also not a field. But let's look at the next step, which is the rational numbers, which are all fractions. And so it's p divided by q, such that p and q are from z. Now, it's not a good definition because, for example, 1/2 and 2/4, by this definition, do repeat because they're the same number. So I'm not gonna get into all of that jargon. But this is a field. You can check and see to base all the laws of a field. Although, again, this is not a good definition. One of them, for example, P is from Z and Q is from N, so that we don't get stuff like 1 divided by 1 is the same as -1 divided by -1. And also that their GCD is 1 and all of that, so that we don't get the repeating of like 1/2 and 2/4. But we're not going to get into that, since this is not a good definition. Don't keep that in mind. But this is a field. Now, next step is the real numbers. So, stuff like 0, 1, pi, square root of 2, e, 3/4, negative square root of pi to the e times 54. All of that stuff. So all of the real numbers. Is this a field? Well, you can actually easily see, yes, pretty much all the definitions of the real numbers do tell us that, yes, this is a field. Now, is there another set that is even bigger? I'm not gonna check whether it's actually bigger, because that's not that territory yet. It's different kinds of infinity, and we're not gonna go down that rabbit hole. But the next step is the complex numbers. That is, includes real numbers like 0, 1, 2, 0.5, but also stuff like I, square root of 3 plus pi times I, stuff like this. All complex numbers. Basically a plus bi, such that a and b are from R. Well, yes, this is a field, but the definition of this and how we define I and all of that, usually people say, well, we don't have a solution in the real numbers for x squared is equal to -1, so let's make up one an imaginary number, I squared is equal to -1. But that's not good. Who told you that there can ever be a solution to this equation? Let's take a different equation that doesn't have a solution in the real numbers. X is equal to x plus 1. Now let's take a number j that obeys this. J is equal to j plus 1. Cancel j from both sides. We get that 0 is equal to 1, and contradiction. Such j's cannot exist. So this is not a good way to tell you what is I. So the actual beginning of complex numbers is actually by taking pairs of numbers, A and B, and then letting I equal 0, 1, and then showing that all the adding and multiplying all works in a field, and just like and also works just like we expect it to, like sums and products of normal numbers. But that's another deep rabbit hole that it won't go into. But if you want to, you can try it and do it, or maybe look it up and see how you properly define the set of complex numbers and show that it's a field and all of that stuff. But that is it. If you want more explainers and other interesting problems and stuff like this, please subscribe to my channel. I'll be uploading more things like this in the future. And finally, that's it.